We're going to start with parallelograms. So we're going to look at a general parallelogram. Oh, let's see. Definition of parallelogram is any quadrilateral with two pairs of parallel sides is all we need. To get a parallelogram, we just need a four-sided figure with two pairs of parallel sides. That's all the definition of parallelogram says. So examples of that might be kind of your standard one. And your classic parallelogram drawing would look something like this. It could be, how about I'll draw it kind of upright or rotate it however you feel. But the important part is it's a parallelogram only if it has two pairs of parallel sides. Okay? No more, no less. Okay? If we have pairs of parallel sides, oh man, you spent a lot of time back in the first trimester looking at properties of lines that are parallel and all the angles that are formed and all the relationships that you get in there. We're going to apply all that stuff to these quadrilaterals that have two pairs of parallel sides. Our first two applications are the following. I don't know why this is so big. But our parallel sides theorem says the following. It says that in a parallelogram, opposite sides are congruent. In any parallelogram, the opposite sides are congruent. And similarly, in a parallelogram, opposite angles congruent. Okay. Are two theorems that we can come up with. And in fact, they're really not all that difficult to prove. So for example, in this parallelogram, any pair of opposite sides are congruent. So these two sides are the same length. Those sides are the same length. Does anyone have an idea, just as a thought? I don't think we're going to spend really much time today like actually explaining why this theorem should be true. Does anyone want to take a stab in the dark as to like why it should be true? How do you explain it? Yeah. Well, it has a lot to do with that. Kind of the big idea for why any of the proofs for like why these theorems would be true is predicated on the idea that you could just split this into two triangles. And then because of the parallel sides, as Alyssa just said, you get alternate interior angles here, you get alternate interior angles here, and notice you have two triangles with angle, side, angle congruence. So then all the parts are congruent. Corresponding parts of congruent triangles are congruent. CP, CP, You can prove these two triangles are congruent, and you can prove all the sides all the corresponding sides are congruent. So this theorem follows from drawing a diagonal and looking at the alternate interior angles. And so it's the exact same proof for this. You do the same thing, and then you just claim all the other angles are the same. Then you claim these sides, these angles are the same. Then you claim these angles are the same. It's the same proof. Okay. But they just actually does come from somewhere. It's not just me waving a wand and telling you the parallelograms are the same. So if I say find the missing angles and sides, what are write two equations you could use to find, say, the missing pieces? Opposite sides are equal in length. Okay, there's one equation. And what else do we know? Ben? Opposite angles are equivalent in measure. Would be two equations you could set up, and you can solve each of those to find the values. You get what? It's Q is 9, and you get P is 62. Okay. If you haven't already, do the same for B. Find C and D in our second example. Another idea. Say we have a parallelogram. Say we have a parallelogram. We want to talk intelligently about the consecutive angles in a parallelogram, or the angles that are next door to each other. What should be true about the consecutive angles in a parallelogram? What should be true about these guys? Drew? They add up to 180. Why must they add to 180? Any ideas? Lane? Because they are co-interior. There is something more. They're missing a phrase in there. They're not co-interior. They're something interior. It starts with a co. Consecutive interior angles, yes. Yeah, co, yes, co. Consecutive. They're consecutive interior angles. And for parallel lines, consecutive interior angles are supplementary. And notice that no matter what angle pair you pick, you get consecutive interior angles for a pair of parallel lines. So the consecutive interior angles theorem just says that any consecutive angle pair in a parallelogram is supplementary. Any consecutive angle pair, any two angles are always supplementary. These two things, or you can say measure, how about 1, 2, 3, and 4? 1 plus 2 is 180, 2 plus 3 is 180, 3 plus 4 is 180, 4 plus 1 is 180. So if I give you one angle in a parallelogram, you should be able to find the rest of it. If I tell you it's a parallelogram, I tell you one angle, you should definitely be able to find the rest of them. Okay? This one's got to be, what, 61? And then from here, you actually don't even need to do any more calculating, because we already know that opposite angles are congruent in a parallelogram. So therefore, this one must be 61, and this one must be 119. So then what are the angles in this one? What's the measure of, say, angle J? 78. Okay, Brett, what's the measure of angle K then?
100.
Nice. And so then what's angle M? Fire up. Oh, super awesome. Okay. Parallelograms are also pretty neat because we can actually talk intelligently about their diagonals as well. This is a kind of a cool theorem that is true for all parallelograms. And it says the following, that the diagonals of a parallelogram bisect each other. What's it mean to bisect? Cut in half or intersect at the midpoint. Does it say, do we know that the diagonals are congruent to each other? Are they necessarily the same length as each other for a parallelogram? The same thing about them being the same length? No. What does it say? Okay, sure, we can be literal here. In your own words, what does it mean? That they cut each other in half. So that in our example, it does not say necessarily that h minus 8 is the same as 15. What it does say is that this chunk is equal to this piece. It also says that this piece must be equal to this piece. Notice that these two lengths, even in this example, are not the same. 12 is not equal to 15. This diagonal's length must be 24. This one's length is 30. They're not individually necessarily equal to each other, but they are cut exactly in half by each other. So these pieces are the same, and those pieces are the same. So you get h is 20, and you get g is solve this guy on your own.